Right, Internet Protocol version 6, IP, small b, and 6. What it is? Can you brief me what you understood when someone says, or when I say IPv6? What comes in your mind?
Yeah, IPv6 is like because IPv4 is going to be like the number of IPv, the internet is getting bigger day by day, and the number of IPv4 public IP is not that much huge because so this is the reason INA researcher then designed this IPv6, which is like 120 bit. So the number of IPM, I mean the public IP we can get from like the huge, I mean, it's like massive number.
Well said, well said. So IPv4, the number of IP addresses that you get out of IPv4 is very less, but the internet grows. Internet has grown very fast, very big. So there is no sufficient enough of IP address. For this reason, you want another version which can support more IP address, and it is 128 bit size. Binary bit size. We have 128 binary bits with which you can have enough, more than enough of IPv6 IDs. IP address is basically an ID to identify the device that we know. IPv4 is only 32-bit, only 32-bit binary. With 32-bit, it can only produce less number. With 128-bit, of course, it can produce more numbers. 32 and 128, that's a big difference. To understand the difference, I always used to say this. Let's say you got 3 bits. With this 3-bit, what are all the possibilities you got? 0, 0, 0, 0, 0, 1, 0, 0. Likewise, if you say 1, 1, 1, this is 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. And what is the result you get? The face value of all these 3. Okay, face value of this will be 4. Face value of this will be 2. Face value of this will be 1. What is the total face value you get?
8.
Is it 8? 7.
Sorry.
So you got 7 different possibilities. 0, 0, 0, 0, 0, 1, 1, 0, 0, like this, no? 0, 1, 0, 1, 1, 0, like 7 you got. And if you had just added another 1 bit, possibilities are going to be doubled. This is 2 to the power of 4, this is 2 to the power of, 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, 2 to the power of 0. Now when this bits are on, the face value here is 8, 4, 2, 1. What's the total face value?
8 plus 4, 12. 12 plus 2, 16 is 15.
Now you see, Just adding one bit, I got doubled. Earlier it was 7, now it is 15. Just one bit can double the amount of IP address that you get in IPv4. If you make it as 33 bit, today the entire world is surviving with this 32 bit. If you would have made 33 bit, it would have doubled what you had. You can have another planet with IP address. Just adding one bit extra, it would have doubled. Or if you would have made it as another one, let's say for example this is giving 6 million, this would have given 12 million. And if you would have made 34 bit, it would have given 24 million. And you might have said, ah, wonderful, we got too much of IP address. Let us make it as version 5 IPv4, IPv5, IPv5. They tried this actually and made a version called IPv5. Later they said, no, no, no. What if some big technology comes like internet was not at all even, in the mind of people like 30 years back. Yeah, no, I cannot say 30 years back, 40 years back, 35 years back. It was not in the mind of people. It was just in few labs. They were connecting their own uh, military departments. They did not imagine this big. But later now it has come to the hands of every Kupan and Chopan in a village, which they did not imagine. What if something like that comes in future, which you cannot even think now? We need an IP address for future technology. So they said, let us go to 128. And that we will call it as IPv6. So this is the story behind 128 IPv6. They do not want to take chance again. They don't want to simply limit with a small number like 34, 33 bits and have as a version. They made it as 128. It is too big. Too big, too big, too big. How big? It is said that every single square feet of earth you can provide an IPv6 address. I am talking about every single square feet of earth, not only the land, the waterways, the mountains, everywhere, every single square feet of earth, you can provide an IP address. Every single square feet of earth can have an IPv6 address. That's what you need, right? To control the entire world. Say, sometime, people say one world order, one government, one nation, one world, one government. For that, what is needed? This is what needed. Anyway, soon you'll be having robots as traffic police, as this and that. And robots can be controlled through Wi-Fi signals. They will have an IP address. You need to select the robot, otherwise the robot is going to hit you back. It's going to hit you. So we see every square feet of an earth can be given an IP address so that you can control every square feet of earth. That's the main intention of we having internet. controlling the world. Yeah, we are going towards that. It's the final target. We want to have control over the whole world. Means not me, not you, the human race wants to control the whole world. So this has come. IPv6 contributes to those ideas of the future governments. So they are really working on it, and IPv6 is one of the contributing thing for their ideas. Now, where are we? 128 bit, is it enough? Of course it is enough, too much. And someone also said like this, according to the today's technology, only 5% of the 128 bit address can be used. We don't have technology to use more IP addresses. IPv6 is that big. Only 5% of the addresses can be consumed. Now, if it is so, is there any need for private IP address? No. The reason why we have private IP address and public IP address in IPv4 is to save some IP address. If everyone is provided with a public IP address, we will not have enough IP address. So, in an organization, you may have 2,000 computers, 10,000 computers, but you don't need to buy the 2,000 or 10,000 IP address. You can use private IP address and you can NAT it to public IP address. That's where NAT comes into picture. So, in IPv6, there is no NATing because why? Because
All are public.
all are going to be public because you don't need private IP address. You have enough of IP address. You have enough of IP address. Every single person can be given, somewhere I read, 10 to the power of 7. How big number you will get. Each person can be given this many public IP address. Every single person can have this many public IP address. So it is like every bone in your body can be assigned with an IPv6 address. Every bone. You see? So why you need private? No need. If there is no private, why there is need for NATing? No need. Right? So this 10 to the power of 7 is a big number for a person. That many IP address is really big number. So there is no need of NATing, no need of private. All will be in public. Is there any problem in being public? It may sound like a problem. Everyone is in public. What if someone attacks? Everyone can see me. What if someone attacks? See, when we are growing, definitely there will be a lot of attacks. But we also have a power to resist against the devil. We also have the power. In networking, what is the power? Firewall. You have firewalls. That is why you need firewall. So because of attacks, you cannot hide behind a NAT. That's not a good idea. Yes, I am public, but still you cannot touch me. That is real, stable, reliable network. Even if I am public, no one can attack me because my firewall is there. You see, that's the job of firewall. If you use firewall properly, then you will not worry about being in public. Every single device will be in public. Today, your cell phones are public. You know that? You accept it, right? Without even questioning, you accept it. Like my Google shows 1 year before you were in this place on August 25th. This is the exact place where you were staying. It shows even the picture where building where I was staying last year this time. Sometimes it shows even 5 years before where I was going on this date. I'm already in public. I did not question. And no one gave me advice or no one asked me, can I put you in public or not? They simply put me in public because I'm using cell phone. I'm already in public. Everyone is in public. Then why you hesitate network? So all that you need is a good firewall. That's a bad idea saying no, IPv6 is not safe. That's a very bad understanding. Show me anything safe in IPv4. So this is the truth behind networking. You are public. There's nothing private. You need to secure yourself with firewalls. That's why the firewalls are more important today, because everyone is in public, they cannot avoid it. All are in IPv6 today. Do you think you are not in IPv6? You are already in IPv6. Your computer may not have an IPv6 address, but your ISP carries your packet using IPv6 encapsulation. Your question was, when I have IPv4 address, why do I have again IPv6 address? Why should I have both? So that's a good question. Why should we have both IPv4 and IPv6 in our computers? Answer is, see, there are some services our computer takes. Some computers take IPv4 service, request for an IPv4 service. Some computers request for IPv6 service. Some computers says if IPv6 service is available, I'll take, if not, I'll try IPv4 service. For example, I'll tell you one thing. In your browser, if you say yahoo.com, both requests will go. That's an example for a service that requests for IPv4 first, DNS request for IPv4. If DNS request for IPv4 is missing, still you will have internet, you will have the web page because it's going to request IPv6 also. I repeat, when you type yahoo.com, your computer will generate two DNS requests. One is IPv4 DNS, another one is IPv6 DNS. It will say, hey, is there anyone called yahoo.com? Give me the IP address. It will ask the IPv4 guy, IPv4 DNS. It will also go to IPv6 and say, hey, you know anything about yahoo.com? If so, give me the IPv6 address of yahoo.com. You see, if Yahoo stops IPv4 web service, customers will start using IPv6 Yahoo service. So this is a migration period. During this migration period, both IPv4 and IPv6 Yahoo is available. But soon, IPv4 will be stopped. And only if your laptop supports IPv6, you will be able to go Yahoo or Google or Gmail or Yahoo Mail. They will force you. Sometimes you will not know they are forcing you because your operating system, no? When you upgrade your operating system from Windows what? Windows 10, Windows 9, Windows whatever. From there to Windows 11, when you upgrade, your operating system will start prioritizing IPv6. Anything that it wants to download, like updates from Microsoft, your operating system will first go and request IPv6 server and also IPv4. So priority will be given to IPv6 in your latest operating system. In the older operating system, it will try IPv4 and then IPv6 if IPv4 is unavailable. Even the developers, they don't now send patches for their softwares in IPv4. They stopped IPv4. They send only patches for those IPv6 running machines. For example, you buy a microphone, very costly microphone to use with your laptop, and that needs a driver. Now the driver is going to get the update from the vendor, the the microphone vendor. It goes to the microphone vendor with IPv6 request and asks for software upgrade. All right. If your PC don't have IPv6, then you will not get upgradation. You will not get the latest patch. You will not get the advanced feature. So what I'm trying to say is, your question was, why do my computer have got both IPv4 and IPv6 address? This is for time being. You will see both because some of the services are still in IPv4. They are not providing in IPv6. Some services, they're already in IPv6. They do not want to provide IPv4. Some vendors, they have got services for both IPv4 and IPv6. So as a user, end user, you need service. You don't care whether it is IPv4 or IPv6. IP.
Yeah, it's right. At this moment,
Mhm.
still in production environment, some very old computer like XP, Windows XP. In production environment, Windows XP, I think they stopped giving the service to for the home user or the single user. But in production environment, still Microsoft providing the service for XP or some older version. Those operating system.
So that's correct. So vendors, they're migrating to IPv6. Some are still in the pipeline. Some are yet to start. But the end customer, they should not be denied service because of the simple IP address. What is IP address? It's just an ID. So for time being, for another at least 10 years, you will have both IPv4 and IPv6, so that you will not get disappointed with any of the services. Okay. Now we saw IPv6 is 128-bit size, and so far what we have seen is there is no need for private IP address, and there is no NATing because you don't have private IP address. You no need to do NATing between any address to any other address. But later on, you will be learning something called NAT PT. This is not normal natting. You should not think, he said no natting, but why he's talking about nat? No, this is not nat, simple nat. This is not simple nat. This is nat PT. We'll be seeing this later. Protocol translation. It is not address translation. Of course, it's going to translate some address, but it is not like normal NAT. Normal NATing is network address translation. You translate from one IPv4 address to another IPv4 address. That is normal NATing. Both are IPv4 there. Here, it is protocol translation. Translation from IP to IPv6. This is one protocol, this is another protocol. That is what NAT PT is. This is not at all a recommended solution. You see, Rahman's computer has got both IPv4 and IPv6. You know why? They don't want to do this. Let's say their ISP is IPv6. And this is Rahman's computer. And there is a router here having IPv6. And his organization is in IPv4. Let's say it is only IPv4. Now what his company would have done is, they would have done this NAT PT as a solution. Take the IPv4 packet, translate it to IPv6 and send. But they have not done this one. Why? Because this is not really good. NAT PT is not good. So what they have done is, in their organization, they say, I will also run IPv6. Wherever IPv6 is needed, let it use IPv6. Wherever IPv4 is needed, let it use IPv4. They don't want to do translation. Alright, this is what called as dual stack. What Mr. Rahman's computer has got is what called as dual stack. Both IPv4 and IPv6 running at the same time on same port. Dual stack. This is the best solution actually. Easiest as well as best. It is best not because it is easy. It is actually best. And it is easy also. Run both IPv4 and IPv6. NAT PT is not a good solution. Why? You need to understand the seriousness here. You are translating the IPv4 into IPv6 and IPv6 into IPv4, which is very difficult and very process consuming one. I'll show you why I'm saying very difficult. I'm not saying it's going to say it's very difficult. It will do it for you. The translation, when you enable NAT PT, it will translate from IPv6 to IPv4 and vice versa, no doubt. But with very heavy process utilization. Why? Let me show you. If you see here, they're totally different. The header is totally different. This is IPv4 and this is IPv6. Is there any match in this? You tell me. Version is matching. Source address is matching. That also don't match. Here it is 128. Here it is only 32. It is only 32. It is 128. Is there any match? Then how you are going to translate? What will happen to those fields when you translate that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match? What will happen to those fields that don't match?
Yep, they will go with the same format with IPv4.
All right, now you see something called fragment set, which is not allowed in IPv6. Then what will happen to that portion of the header? Or when you take from IPv6 and give to IPv4, IPv4 says, I want to have fragment offset, but where is the information? No information. So it's going to be, see, it will work, but with very difficulty it will work. A lot of junk fields it will fail, and those things need to be processed. This is CPU consuming, time consuming, pressured job for the devices. You cannot use this for a long run. Performance will be going very down, bad, very bad. Performance will be going very bad, going down. It won't be good. High CPU utilization, not good. There's no comparison. You know, you take one. You take one. What I can say? You take one Maruti 800, and and you take one BMW, whatever the model that you have, latest, and you are trying to say this is that and that is this. This is also a car. This is also a car. Oh no, not possible. Very long, very big difference. Very big difference. You cannot say this is also a car, that is also a car. This too may be a car, but this is not the same car like Maruti 800. Something very, very big. So NatPT is not a simple word. Very bad idea. Very bad idea. See, this is possible, but not a good idea. That is why you have dual stack, so that you no need to translate. Why you need NatPT? Because you have only IPv4. You want to route it in IPv6. Then you do NatPT. What if you also have IPv6? There is no need for translation. You use your IPv6 to talk to IPv6. You use your IPv4 to talk to IPv4. No translation either. See how easy and simple solution called dual stack. We will be talking about these things later. Because Rahman asked this question, I took this. We'll go back to those things later. Now let's go back to our place where we left. IPv6 is 128-bit size. There is no need for netting because you have enough of IP address, too much of, not enough, too much of IP address, more than sufficient. So what we have to do is we have to see the bugs in IPv4 and how it is eradicated in IPv6. See, bugs in IPv4 is this: always sending a broadcast. If you take IPv4, there are a lot of services that uses broadcast as a solution. Can you name one or two?
Sorry, what's the question?
In IPv4,
Yeah.
using broadcast for some services is considered as a bug. It's considered as a wrong approach. Can you name any of those wrong approach that we have in IPv4?
The ARP request,
Yes.
ARP.
ARP is one of the service. Very nice. Any other service?
DHCP.
DHCP is another service. Any other? Okay, this too is enough. A very good example. So you have,
REAP version 1.
yeah, in routing protocol version 1. Okay, there are a lot of other services, but frequently used services are broadcast and ARP. They do broadcast, sorry, ARP and DHCP. They do broadcast, which is very, very bad. A lot of attacks are possible because of this broadcast. When you say who is 10111, because you are sending us broadcast who is 111, attacker will say it's me. That's a man in the middle attack. It is because of your broadcast, man in the middle attack is possible. You should avoid broadcast. Yeah, avoiding broadcast will close the doors of attack. Many doors that you have kept open can be shut. Many doors that are reason for the attack can be shut down if you stop using broadcast services. ARP is one nice example. We have to shut the doors of ARP. We have to shut the doors of DHCP because they're all dangerous. They open the doors for attackers. We have to shut those doors. IPv6 have shut the doors of those services. How? There is no ARP in IPv6. If no ARP, what do you do to learn the MAC address of the neighbor? With the ARP, what you learn is the MAC address. You resolve the IPv4 address into into MAC address. IPv4 address into MAC address. That's what ARP does. You learn the neighbor's MAC address through ARP. In IPv6, how do you do that? If you don't want ARP, in IPv6, no ARP. If you say, I don't want ARP, then how do you manage to learn neighbor? We use ICMP version 6 neighbor discovery method. And this will use only multicasting. Multicast. So in IPv6, we are not going to do broadcast. We are replacing with multicast. Multicast is not bad. Multicast packets are delivered only to the group member, not to the attacker. Only those legitimate groups who are supposed to receive the ICMP version 6 neighbor discovery. See, neighbor discovery. What is neighbor discovery? Learning the neighbor's MAC address is neighbor discovery. And it is done by using a special IP address called link local address. So no ARP. Instead of ARP, we use ICMP version 6 neighbor discovery that uses multicast and link local address. It's the same story with DHCP. No DHCP. No stateful DHCP. In IPv4, the DHCP that you have is what called a stateful DHCP. Why? because the DHCP server will take your MAC address in a table. It will save it in a table and say, for this MAC address, I'm giving this IP address. That's what stateful. It keeps a record of who has taken what is his MAC address and what IP address I have given him. Those table recorded in DHCP server is what stateful. In IPv4, it is stateful DHCP. In IPv6, stateless. In IPv6, it is stateless DHCP. IPv6, it is stateless DHCP. What it is, there is no record of who has taken what IP address. We'll talk about that later. We also call it as auto address configuration. Auto address config. Auto address configuration. Auto address configuration is nothing but stateless DHCP. We'll talk about that later. So wherever the broadcast was there in IPv4, there was a possibility of attack. Now those doors are shut in IPv6. IPv6 is truly a safe protocol compared to IPv4. Every firewall now has developed the signatures to identify IPv6 attacks. See, after closing a lot of doors, the attacks are reduced. And for those few attacks, you have signatures in the firewall to identify and mitigate them. So when you compare IPv6 to IPv4, IPv6 is the best, even in security. Don't think that there will not be any firewall for these long days. We were using ASA firewall, we were using PAN, file alternative firewall. The developers have developed those firewalls for IPv4 attack. No, that's a silly idea. See, identifying attack in IPv6 is much easier than IPv4. How? You already saw. See this header itself will show you. See here, how many headers are there? Here it is very simplified header. Here you can easily identify something than searching here. Yeah. So IPv6 don't support broadcast, or any service that uses broadcast is not supported in IPv6. Instead, it uses only multicast, unicast, and anycast. Multicast, unicast, and anycast. Multicast means what? Identifying the group and delivering to the group. Unicast is what? Identifying an individual device and delivering to that device. Anycast is what? Identifying the nearest destination and delivering it to it. For example, you want to withdraw money. You do anycast. You know that? You want to withdraw money from ATM. You always do anycast. You don't do unicast. You do anycast. What do I mean by that? You see the nearest ATM. Go and withdraw. What if the nearest ATM is closed? You will see the next nearest ATM. Now you go where? Second ATM and withdraw money. If the first ATM is open, you would have not gone to the second ATM. Only if the first ATM is not providing you service, you go to the second nearest ATM. This is what called as any cast. Going to the nearest destination, closest to destination. If the destination is unavailable, you go to the next closest. I'll explain you the example later when we go to the lab. IPv6 only has got these three, no broadcast support. All the multicast address will start with FF02. FF02. Colon, let's say 5. This is 224.0.0.5 equivalent to this. In IPv4 for OSPF, we have this. Here in IPv6, it is FF02::5. In IPv6, FF02::5. In IPv4, it is 224.0.0.5. In IPv6, FF02::A. Can someone tell me what IPv4 multicast address and what will be the protocol?
IPv4 multicast address is 224.0.0.0 to 239.2.
No. Equivalent to this. Sorry. Equivalent to this. Equivalent to this in IPv4 is this. What is the equivalent to this? 10. A means 10.
It's 10. A means
Which
10,
protocol?
Yeah. This is IGM Internet. Yeah, this sorry, this is IGRP. Okay. Sorry, EIGRP. Yeah, EIGRP.
In OSPF, you also have 6.
224.0.6.
This one is RIP-NG. Here we call this RIP NG, next generation. Here you call it as RIP version 2.
224.0.0.9.
Yeah? Fine. So this is the multicast addresses. Let us talk about unicast address. Unicast address will always start with some 2000. It can be 2001 or it can be 2000 or 2002. It depends on the region. Depending on the region, the first number will vary. I can say depending on the continent. I said you got unicast address, you got multicast address, you got anycast address. Anycast is one to the closest. Multicast is one to the group. There are well-known groups, and some are transient, some are solid-state network node. We'll discuss those multicast groups later. Unicast, some are global unicast, some are link local, UBAC, unspecified, unique local, embedded. This is nothing but an address that you used to reach, like a public IP address, starting with 2000, 2001, 2002. This is for neighbor discovery, link local address. It will always start with FE80. Link local will always start with FE80. This is a loopback interface address. Sorry, not the interface, loopback address. What is the loopback address in IPv4? What is the loopback address in IPv4?
1.1.1 something. Sorry, I mean, sorry, what you said
Loopback
that
address, not
process.
loopback interface. I'm talking about what is loopback address in IPv4.
Oh, the loopback address is something like to
Yeah,
test
what
the
is the reserved IP address?
system. Like
Reserved range for loopback?
oh, 127 dot
Yeah.
0 dot 0
Instead
dot
of
1.
127.x.x.x, x can be any number, you have just only one. Look at this, how wonderful is IPv6. In IPv4, we have wasted lot of addresses unknowingly. 127 anything is a loopback. It is not necessary. Or Rahman was saying, loopback address is for testing. Why do you need um, lakhs of address for testing? Only one address is enough. Maybe this is enough. Which one? 127.1.1.1 is enough. Why you have any number here? 2.2.2, 1.1.25, 1.25.1. Why we have wasted this 24 bits? We have wasted. In IPv6, you see, this is the only number, fully masked 128. This is the only address that is meant for testing. Say, for example, ping ::1. See, I get reply from ::1. Zero packet lost. All 4 sent and 4 received. Beautiful. You don't now waste any unnecessarily. Just only one address given for. Likewise, for unspecified meaning any, you don't know, which means any. This is unique local address FC00, which is no more supported, removed from the standard. FC00 and FD00. Earlier they were having a unique local, like a private IP address, unique local, but it is no more now, removed from the standard. Embedded address, this is for encapsulation. We'll talk about that when we do 64 tunnel address types. Okay, as I was telling earlier, the unicast address will always start with 2000. It can be 2000, it can be 2001, it can be 2002, it can be 2003. It will not start with 3000. That's what I mean. It will always start with 2000 as per the standard. It is starting with 2000 only. Anywhere around the globe you go, IPv6, you will see only 2000. Always you will see only 2000. Only this number will vary depending on the region. They are already given, reserved for various regions. Now, if you take any IPv6 address, it's 128 bit. How it is divided? 128 binary, I said binary bit. It's binary bit, 128 binary bit. This 128 binary bit is divided into 32 hexabit into 8 hex date. Meaning what? You cannot write in binary 128 like this. It will be too much. It will go full page. One address will be one full page. No, just 32. 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 30. This is IPv6. 32 hexabit. This 128 is written in hexa When you write 128 binary bit in hexa, it will not be 128, it will be only 32. How? I'm going to explain in some time. But now what I want to say here is, you no need to write 128 bits. You just write 32. Only 32. And it is in hexa. So the size of the address is reduced because you are using hexa. If you would have used binary, it would have been a big number. See, IPv4 is binary. But do you write in binary? No. You write what? 10.1.1.1. It is easy for you to write. You are not writing 32 binary address. I never write 32-bit binary address to any computer. I never wrote in my lifetime. But I know IPv4 is 32-bit. But we never used it. We convert it into decimal and we use it because decimal is the number we use it. Hexadecimal is much better than using decimal. Hexadecimal can make your address more smaller than a decimal. If you will write in decimal, it would have been 64 decimal bits. Because you wrote in hexadecimal, it is only 32 hexabits. We'll talk about that, how 128 has become 32. Now this 32 is divided into 8 groups. If you need to divide this 32 into 8, 32 divided by 8 is what? 4. So after every 4 hexabit, there is one division, one colon. That's it. Okay. After every 4 bit, you have a division. Yeah. So this is how it is structured. You see, there is a connection between IPv4 and IPv6. IPv4 is 32-bit, but here IPv6 is 32 hexabit. In IPv4, how many bits in an octet? How many bits? 8-bit. Here also you have something 8, but here it is 8 groups. Hexadate. Hexa numbers 4 in a group. This is one hexadate. This is another hexadate. How many you have? 1, 2, 3, 4, 5,
Yeah,
6.
one octet,
One
16 bit.
hexadate is 16-bit. Right? This is 4 binary bit. One hexadate is 16 binary bit. 16 multiplied by 8, no? I have 8. 1, 2, 3, which is 128. Right? So how this is 16 binary bit? Because, I repeat, how this is 16 binary bit? Because there are 4 hexabits. One hexabit is
32 binary.
4 binary bit.
4.
Now you see, if one hexabit is 4 binary bit, 32 hexabit is 128. That is why I said 128 binary bit is written in 32 hexabit. If one hexabit is 4 binary bit, here I have 4 plus 4 plus 4 plus 4, which is 16 binary bits in one hexadate. 16 binary bits. All right. Here, the IPv6 address is 128 bit, and we got 1, 2, 3, 4, another 4, so totally 8. Totally 8 we have, and it is 128 bit size. In which 64, which means right here, is about the network. It is about which continent, which country, which ISP, those infos, which network. We call it as global prefix. It helps to identify the location from where the traffic is coming. Global prefix. This is 64 hexabit. The other 64 hexabit is called as interface prefix. This is other 64 hexabits. So totally 128 binary bit. Sorry, yep. I should have not written hexabit here. So the 64 binary bits. Okay. 64 binary bits. 64, 64, 128. So the network, it won't cross this boundary. As per the standard, it should stay less than this. But you see, only the network portion alone is 64 bit. What is today's IPv4? Only 32. Just network portion alone is 64 bits. Too much. In each network, interface portion alone is 64 bit. It's too much. Let's say we have an address. $2,000 colon let's say this is the address. You don't need to write these many zeros. This 0 has got value. If you remove that 0, 0, 0, then it becomes 2. You should not remove. But this 0 has got no value. 0, 0, 1 means what? 1 only. So you can write 2000. Instead of all these zeros, you can say simply colon, colon, and then 1. Okay. Yeah, let's say you have some number here. Okay. Then what you can do is you can put colon colon either for this, that's recommended, or for this, anyone. So I can say 2000. For this you will put 1 0. For this you will put another 0. Leading 0 no value, put A. And this consecutive 0, you can put simply open colon, no 0 there. And then this one here. This is how you can simplify and write. If you write like this, it will understand like this. Yeah. All right. So